All right, welcome everyone to Papers We Love 2 Online Edition. Today I will be talking about the paper Liquid Data Networking. This is a paper that inspired me, not so much because I had a love for liquid data networking, but because I have a deep hatred for TCP and believe that TCP is a protocol that was in some sense designed to make engineers suffer and cry. So when I ran across liquid data networking, I was like, this is a protocol that is profoundly not TCP. I want to go and share this with the internet and my community. So who am I that you might actually be interested in listening to me speak? I have a history of working on a number of different distributed systems. I did research at Georgia Tech on distributed systems, mainly in surveillance-resistant tools. How do I build a network where I have some adversary that's trying to destroy my network? It turns out that if you assume that someone is deliberately trying to destroy your network, this is a pretty good model for the conditions on the internet today, because everything will fail and you end up building more robust systems if you just assume that not only is everything going to fail randomly, but pretend it was malicious. That's probably the design you want, is to think that your hardware is actively trying to delete your data. From there, I went to Google and worked on the YouTube team and switched sides from working on censorship resistance programs to censorship programs and making sure that people couldn't violate the terms of service. From there, went to a couple of startups and tried my hand on the how to run infrastructure with very little resources. And I can tell you, life is easier when you are at Google than when you are at a tiny startup and trying not to spend any money while running your online services. Went to C-Cell, ran a web app firewall company where I learned a lot about actual protocols and what goes on in the internet. And it is amazing when you just stand up a server and start watching the traffic, the kinds of things that knock on your door, no matter who you are. Currently, I am at Twitter, working on their security team. And again, Twitter is a large system and we have to get distributed systems right, or we will be crushed under the weight of our own users. But what we're here to talk about today is liquid data networking, which is a form of forward error correction. It asks this question of, what if we try to solve the networking problem and we try to solve it in a way that is not, I'm going to go back and repeat what I said. So the fundamental idea in TCP is, oh, you didn't hear something I said, tell me that you didn't, whatever the last thing you heard was, and I will go back to that point. The goal here is to say, okay, let's turn this around. What if I don't want to repeat exactly what I've said? Can I build protocols that work better? So there are 4 types of efficiency that this paper is particularly focused on solving. The first is signaling overhead. If I want to not have this go back signal, where I simply say, I'm going to go back to the last thing I heard and start replaying, I'm going to have to tell you specifically, this is what I've heard and this is what I haven't heard, and how do I get new things? So how do I keep this overhead low so that I make sure I don't have to be overly specifying of what I got and what I didn't get? The second is latency overhead. When you have something like TCP and you stop and say, what was that, and repeat it, the protocol can't move forward. So you get these halts where like you're going on and then it stops. And then you're going on and then it stops. And then you're going on and then it stops. Can we get a better latency, less jitter, cleaner signal? The third is security overhead. We want to make sure that in this system that nobody can lie to us, but we're also not spending an over amount of energy trying to verify all of the data that we got. We want something that is similar to the TLS levels of authentication, where you just have an HMAC and you can make sure that you got the right content. We have response overhead. We don't want to repeat ourselves too much. If I'm using a go back protocol and you send me 100 packets and I missed the first one, I go back and I send those 100 packets again. Well, 99 of those packets were a waste of my energy to resend. You already had that. You had only missed the one. So can we do better on this wasted repetition? And the last one was storage overhead. Almost all of the techniques that are used in this paper involves using more processing and more storage and more bandwidth to solve all of the problems we get of having to go back and repeat. But as I like to say, I've looked at the internet and the future trends, and it seems pretty clear that processing power is increasing, bandwidth is increasing, storage is increasing, and the speed of light is staying the same. So if I can pay some processing, bandwidth, and storage in order to prevent a round trip, that's a win. I really want to make sure that I am avoiding those speed of light constrained parts of my protocol. All right, so there's 3 primary ways you can solve the problem if we say we want to switch from a go back and repeat protocol to an erasure code protocol. Fundamentally, what erasure codes give us is I can lose some of the data and still recover the message. So as opposed to a traditional, I send you 100% of the message, you tell me you missed something, and I retransmit the thing that you've missed. With an erasure code, I say, I'm going to make the message 110% as long as it needs to be. And as long as you have received 100% of the signal, you can recover whichever pieces of that 110% that you have missed. So I can request specific data and say, hey, I'm missing a particular piece of the protocol. I would like you to give me this chunk. I can request random data and say, hey, every time I need more code, just send me some more code. This isn't quite as good as specific because what if you send me the same symbol? Maybe I have encoded something, broke it into 10 pieces, made 14 erasure encodable chunks. And I ask you to send me a random one. If I already got 9 of the 14, there's a chance you're going to give me one of the ones I had already received. So that may not be useful to me because I already have that symbol. And the last one's to say, I want to send only useful data. So I could tell you, here's everything that I received. What I want you to send me is anything else. So rather than asking for a specific thing, I say, I want anything but the stuff that I've already received. The other properties we want is we want to have cacheability and additivity. So let's say there are 2 or 3 different people who are all trying to download the same file. If my original server generates new random codes for every single person who tries to download the file. So I give you an erasure chunk, and I give you an erasure chunk, and I give you an erasure chunk. Every time I give someone a chunk, it is a brand new object that has never been seen before. This would be totally uncacheable. So no matter what request you requested, you would have to go all the way back to the originating server. This has obvious costs and breaks the way we do the internet today. Like we use Akamai and Fastly. It is a key part of the way we design things to say, I want stuff in cache because caches is how we make things fast and performant. And the second value is additivity. If I say I'm always going to give away the exact same 14 encoded symbols for my block of 10 things, then I'm going to be able to cache it everywhere, and any server is going to be able to grab that symbol and hand out that same named symbol, but it may not be additive. If there are 2 caches in the world, and I go to one of them and say, give me chunks of the file, and I go to the other one and say, give me chunks of the file, I'm going to get identical things from both sides. So there's this tension. If I make very large numbers of symbols, I end up in a world where things aren't cacheable. And if I make very small numbers, I lose the additivity property of I can talk to 2 different caches and say, hey, give me half a file, and they'll add up to one whole file. So the second one is we want to have encoded data protocols. I want this to be bandwidth efficient, where I'm not wasting a whole bunch of extra bandwidth sending things over and over again. I want to make sure that it is cache efficient so that I get the systems, and I want responsiveness. I don't want to have to wait a long time to rebuild my thing. So one of the risks you can imagine is, let's say I encoded a lot of data. I made a multi-gigabyte file, and I break the whole thing up and I encode the whole thing with symbols, but you can't put the thing back together again until you have the entire file downloaded. Now you're going to get a lot of latency because you are waiting for an entire gigabyte of data to come down before you can reassemble the object and get anything delivered. So it's this big all or nothing. We want more responsiveness than that. As we're downloading, it's nice to be able to say, I'm going to start playing the video at the beginning and actually be able to generate objects at the beginning, even though I haven't got the entire file. So the paper goes through a number of scenarios that guide them and say, okay, as we do liquid data, what are the kinds of things we can build where we benefit from having this erasure code, founder code structure to deliver the objects? And the first example they give is multi-hop wireless. Imagine you're in a world where you've got a Wi-Fi router that goes to a repeater, that goes to a repeater, that goes to a repeater, that goes to a repeater. You're 5 hops out, but you still want to be able to get reasonable performance. If we assume that there is only a 25% chance that you're going to lose a packet between any one of these hops, by the time we've cascaded through 5 hops, there's only 23% chance that a packet has gotten through. If you tried to use TCP in this environment, it would not work at all, because you would send the data and it would lose a bunch of the data, and then it would say, oh, I need to stop and go back and send more requests, and acknowledgements would get lost, and it would be going back because it had acknowledgements that he didn't see. The whole thing would just come to a crawl. And each time it thought you missed data, it would slow down even more and be like, oh, I'm losing packets. It must be because I'm overflowing a buffer somewhere. I'm going to slow down and lose more packets. I'll slow down more. So when we think about, okay, what is a kind of ideal behavior that you might expect here is, okay, we're going to use some kind of erasure code, and I'm going to build enough data that even though I'm losing 3 out of 4 packets, I can still deliver it. So I'm going to erasure code. I'm going to make my pile 4 times larger than it needs to be. I'm going to send all of that down, and even though only 1 in 4 packets actually makes it to the end of the chain, there's still enough data there to reassemble my entire object. And at first glance, that kind of feels like that's the ideal, that would be the best that we can do. But this paper says, no, actually, we can do better than that by borrowing an idea from named data networking. So in named data networking, it says, we're going to do this store and forward, where I'm going to pull an entire object to the first router and know that I have it. And then I'm going to put the entire object in the second router, and it will know that it has it. And then I can put the entire object into the third router, and it will know that it has it. But to do this means you're paying a lot of latency, because you have to download the whole object and verify it, and download the whole object again and verify it, and download the whole object again and verify it. That's going to cause a lot of latency. So what liquid data networking says is, why not both? Let's put a hash on every packet so that we can verify a single packet at a time. And when we first start the connection, we're just going to send all the packets through. And every packet that I receive, I'm going to forward on down the chain. So almost immediately, the thing at the end starts receiving the 25% of the file that didn't get lost. But this first router, the first named data node, once it gets to 100% of the file, says, I don't need to ask the node that's behind me to repeat data anymore. I've recovered 100% of the file. I can start generating erasure forward error corrected code objects now. And the second node starts filling up. And once it's full, it now has the entire file, and it can start generating codes over that file. So what we end up is a world where we can start sending data immediately. The node that is at the very end immediately starts building data and is going to have this very low latency performance. And only to the degree that we're actually losing packets does the second node have to receive more than 100% of the file to start sending out extra codes, and the third node and the fourth node. So each node gradually fills up while it's just forwarding traffic along. And then once it's full, says, now I can generate my own erasure objects and my own fountain codes for you to reconstruct with. So we now get the best of both worlds. This is as low latency as it could be, because if we're not losing any data, 100% of the data is going to come through each of the links. It's all going to reach the end, and it's all going to be as fast as it possibly could because it's just sailing right through. And if we have a really aggressive loss, it's as fast as we would get with reassembling everything, except that some of the data gets through initially. So we end up being able to start receiving some data before any node has received the entire thing. So it speeds it up compared to a pure store and forward also. The basic idea here is just every node is filling the cache. We get a nice caching behavior as the node is filling up. And once the node is full, it can essentially become its own source and generate its own data. So the second structure that they talk about is, let's say we're doing some kind of multicast tree. I have one file and I want to send it to lots of different nodes. So in this structure, we have an original publishing node, a bunch of nodes that are in the middle of the network, and then a lot of clients. And each client is subscribing to their nodes and they're forming this nice broadcast tree. As the first node is sharing its packets, those packets can rain down all the way to the nodes at the bottom. And those nodes will be able to start reassembling the file immediately. So again, we get the lowest latency that we're going to get for building up these objects. However, once something like an intermediate node has received 100% of the file, it no longer needs to go back to the publisher node. So let's say this red link here is the only link where we're losing packets. So everyone else receives it smoothly, they get 100%, they recover the file, and this one node here is actually losing its data. It now says, oh, I did not receive the entire file. Let me call back my intermediate node in order to get the packets that I need to be able to fill my entire file. But it already has received the entire file and will be able to generate the additional recovery packets that it needs. So this node doesn't need to say, I got packets 1, 5, 7, and 12. It just says, look, I got 90% of the file, generate a random 10% extra nodes for me and hand me that. And now I'll be able to regenerate the file myself. So it's much lower signaling overhead because it just says, hey, give me an extra random 20%. And from there, it can now rebuild. And each of the things in the node gives us both this nice cacheability and gives us this reusability. If the lossy node were a little higher up, suddenly this node doesn't know what's missing for the people below, but the node that is already full would be able to generate brand new packets to hand to the next node, so it knows that it's going to be useful. But you never have to store more than one of the objects. So if I'm encoding to say 1.3 times the size of the object, and this node is receiving packets, it doesn't actually have to store 1.3 times the size of the object so that it can keep giving packets to the next node. Once it gets to 100%, it can always stop because it knows it can generate as many fountain codes from the packet as it wants, once it has received from the object, once it has received the entire object. The next one they talk about, I thought was an interesting design because it's not a network pattern that we see often now, but I think it comes from the fact that we think in terms of TCP, and this kind of protocol would work terribly under TCP. The idea is, let's say you have a bunch of roadside nodes, and you've got cars that are driving down the road, and they're constantly going in and out of range of a bunch of these very local transmitters. And now I want to distribute some file to all of them, some talk radio station that lots of people are listening to in their car. I can send these encoded packets a little bit to each of several of these roadside nodes. So now each node doesn't need to store the entire set of contents you need to be able to regenerate the data. As you're driving by, you pick up some codes from this node, and then some codes from the next one, and some codes from the next one, and some codes from the next one. And once you have picked up 100% of the segment, you can now reassemble that object and play that chunk of audio. So it doesn't matter whether a car is coming from the left or coming from the right. And some of the cars are going to be moving faster, so they get smaller chunks from each of the router. And some of the cars are going to be going slower, and they're going to get larger numbers of packets from each of the routers. But none of that actually matters, because I don't care if I got 10% from one router and 90% from another, or 50% from one and 50% from another, because the fountain codes are all independent and are each their own unique piece of data. They can all be reassembled to get back the audio. So I don't have to say, have each of these individual routers know what has each car received. It can just transmit its chunk and then transmit its chunk again and transmit its chunk again. And whatever cars happen to be in range will pick up whatever chunks they happen to have in range. You don't even need a back channel at all for the most part. The next one I talk about is load balancing at the edge. Let's say you want to make sure that lots of people who are spread around the country can all download a particular object. If we were to design this network today, we would tend to have to put the entire object in each of the caches. Something like Akamai caches the same object in lots of different places, so lots of different people can download it. And you can try and find your closest node. So if I had, say, 2 nodes that were storing the object, and I picked from the closer one, I would get something that is on average in the right half of the world or half of the country as me, depending on the size of the service area. But if I could have 8 nodes and say, instead of distributing it between 2 nodes and having each of them carry 1 copy of the data, what if I distributed it amongst 8 nodes and had each of them carry 1/4 of the data? This is the same 2x redundancy I had before, but now the question is, who are the 4 closest nodes to me that I can pull 1/4 of the data from, rather than the 1 node that's closest to me? So because I now have 8 nodes, they can be much more distributed throughout my service area. And the 4 closest to me will, on average, be much lower latency than the distance would have been to just 2 copies. So I can use all of my nodes with less storage and get it through. And this comes out with their description of the turkey network as being a particularly tricky one to figure out, where I have one publisher node and I have one node in the middle of the network. It's receiving a bunch of these erasure codes. It's then distributing to multiple nodes. And then you have clients. So the clients can get multipath, and then there's multipath back. This is a pretty complicated pattern. And if we were to try and solve it with TCP, we would have to give up on all of the multipath capabilities and say, I am simply going to pick 1 path from client 1 to publisher node and 1 path from client 2 to publisher node and stream everything through. And we would essentially use twice the amount of bandwidth out of the publisher node. Whereas here we can actually say, oh, because I understand who's asking for data, I can say, I'm going to split my data in 3 different ways and say, I'm going to give you 1/3 of what node EN1 wants, 1/3 of what B wants, and 1/3 of what C wants. And now, when I send this data, once this node has recovered and received 1/3 of each of the things it's sending to its subnodes, it can now reconstruct the entire object, generate new erasure codes, and send it on. So it only needs to download 1x the amount of bandwidth. Why is this interesting? Because it's actually a pattern that you're going to see in distributed networks. If you have some node that is the canonical store, so either I'm stuffing a bunch of stuff into Glacier Store so that it doesn't lose my data, or maybe I have a hard drive on my desk and I store 1 copy of all of my data personally because I know I don't want to lose it. But then I also have a CDN that's trying to distribute it, or a distributed hash table that's trying to distribute it. I can now seed those chunks into this whole network, and those things can cache it. So if there's a lot of demand for my files, I never have to upload each file more than once, because I can fill the network with these erasure codes. And as my stuff gets more popular, it will become more available. And if my stuff's not that popular, well, it can stay in its pieces and chunks. So maybe I upload 1.3 copies of all of my files. and nobody requests them from a long time. And then when someone finally does request it, a lot of that's been lost and there's only 90% left. That 90% can be downloaded from the network and only 10% has to come from me. So I only have to do a little bit more uploading to just push the amount that's in the world back over that 1x threshold. And then the hash table can repair itself back up to that 1.3. So this begs the question, okay, can we actually do this? The underlying assumption of each of the descriptions that I made was I can take a particular chunk of data, split it into chunks that are 1/8 the size of the whole, and I can make a kind of arbitrarily large number of these symbols that any k of them will restore the actual file. We can't go less than a k because each of the symbols is 1/8 of the size of the file. And if I could restore the file from less than 1/8 of the size, I would have violated Shannon's entropy. And I would be able to communicate something that is larger than the amount of data that I'm sending. So the least I could possibly do, a perfect forward error correction, is going to say, I'm going to send you exactly k-8ths of the data. That's 100% of the data. You can repair it. So is it actually possible for me to build some n symbols where any k of the n symbols will let me reconstruct the object? And the intuition for why this is possible, let's talk about using just XOR to do it. So if I imagine that I have a bunch of symbols, and one of those symbols is just, the first kth of the file, and the second kth of the file, and the third kth of the file, and the fourth kth of the file. So I've, in this particular example, broken my file up into 4 pieces. And now I want to say, can I make a large number of codes such that any 4 of them will probably enable me to restore my file? So I'm going to take a bunch of blocks and say each block is going to be the XOR of one of these chunks. So let's say I have the block that is the A XOR B block. And I take the first chunk and I take the second chunk and I XOR them together and I hand you that. Well, now if I give you a bunch of these, it's just a matter of linear algebra. Oh, if I've given you A and A XOR B, you can now recover B by XORing the A block with the A XOR B block. The A's will cancel, you've recovered B. So in general, I can take a thing that's got 3 symbols. If I give you A XOR B and A XOR B XOR C, you can XOR those 2 things together and A and B will cancel and C will remain. This is just solving systems of linear equations. We've all done algebra and been like, okay, if I've got 3 variables and 3 equations, I'm going to be able to solve them. If I've got 3 variables and 2 equations, I won't be able to solve it. If I've got 3 variables and 5 equations, I'm highly likely to be able to solve it. But that only gives me 16 blocks when I broke it into 4 pieces. But let's say I decide I want to be more aggressive than that. So instead of using XOR, I'm going to use plus and say, I am going to give you some number between 1 and 255 times each block. So now I have billions of objects to choose from, where I say, okay, this is 65 times A, and 25 times B, and 32 times C, and 98 times D. As you get lots of these, they're more likely to be linearly independent from each other, and you're more likely to be able to actually solve the equation and get it back. So I hope that convinces you that by using this construction, we can actually get very large numbers of different codes that any k of them will be able to solve. Now, there's some risk if you pick these codes totally randomly that you get k that are not independent of each other. So if I gave you A XOR B and B XOR C and C XOR D and D XOR A, I've created this nice little ring of XORs, but there's no way to actually solve that thing because it just goes around in a circle and I can XOR any of them and get the remaining one. But if I give you one more and it's A XOR B XOR C, or it's just A, or it's just B, or it's just C, or it's all of them XORed together, any of those objects will suddenly turn this ring of unsolvability into a solved problem. And that's what we see in practice is almost always you will find that you can solve and recover the object for either k chunks or k+1 chunks. And it drops off exponentially. The chances that k+2 is unsolvable is much lower than that. And the chances that k+3 is unsolvable is even lower than that. So it just gets vanishingly small odds that something becomes unsolvable. All right. So how do we get the properties we wanted? If I'm just giving away these blocks randomly, how do I know that I'm not going to give people things that are not useful? Or how do I know that I'm not going to ruin the caching? Because I have all these layers of a lot of our examples, you know, the tree, for example, I want to be able to cache objects in the middle as they're going down. And the answer they give is to say, we're going to give a stream object permutation identifier, where we say, okay, for this particular object, I'm going to pick my subset and say, what is the actual k blocks that I'm going to pull from it? And for each seed for some pseudo random number generator, that's going to give me a different mapping from the top to the bottom of which k blocks I actually pull down. So now when I have some network where I care, I can assign each of the 3 en nodes at the bottom here a different identifier for the permutation, and they will each download a different chunk of k files that are highly likely to not be the same k files because they're random. But it's also going to be cacheable. If I'm pulling these files and suddenly the top en node A fails, I can go back to the publisher node and it can give me new objects that it knows aren't the objects that I already have just by serving me from a different permutation identifier. And I can know if I've got a block that is all blocks I've already received by saying, oh, I go talk to the node and say, can you give me this permutation identifier? And they say, no, I only have this other one. You go, oh, I already downloaded all those. I don't need to keep pulling objects that aren't useful. I already got everything that's in your cache because I know, because that was your permutation identifier. Where was I? Permutation identifier. Yeah, so I need to say what object I am trying to pull down so that the network node that's caching the thing can know which packets to give me. I give it a string permutation identifier so that it can tell me how it's downloading things. And of course, once it gets 100% of the file, it can now serve me any string permutation identifier, that stream permutation identifier that I want. Because once it has the entire object, it now knows each of the k pieces, and it can actually generate all of those, this XORed with that. If you ask for something that they don't have, it will just calculate it and hand it to you. So once you have 100% of the file and you have restored the file, now you can magically give away any identifier you want, not just the ones that you yourself receive when you are receiving it. The offset, so you say how far into that particular stream I am, the payload, the actual symbol that you're worried about, and a signature at the end. We need this signature at the end because this way we know who is the node that's lying to us. If we're in some environment and I'm trying to download the file and I'm getting corrupted data as I assemble the file, and it says, no, the actual, I asked for the thing with some particular SHA-256. I assemble my data, the SHA-256 doesn't match. I know I have an erroneous block in there somewhere. So we want to put a signature on each packet that you receive so that I can say, oh, clearly C here has gone bonkers and is corrupting data. Maybe it's got memory problems, maybe it's under a sunspot, whatever. I'm only going to trust the stuff that was encoded by B or A or the original publisher node. And now I can run my reconstruction again and throw out what I believe to be a particular faulty node. Oh, look, now my hashes work. That's a faulty node. I can warn everyone else in the network, hey, this node is faulty. So we get 2 layers of security. We have one layer of security that comes from every packet being signed, so I can know, hey, this particular node is generating bad encodings. And I have the entire object is typically identified by a hash. So once I reconstruct the object, I can go, hey, hash the thing. That is not the object I requested. The hash didn't work out. This is not new to liquid data networking. That's pretty traditional for all named data networking, where it says, hey, I've got some particular content ID. I'm going to pull this thing out of, say, IPFS. oh, this didn't match, I'm not going to go for it. And for redundancy, choosing the K is actually important. So I could, when I'm doing something, say, I'm going to pick a particularly small code. So maybe I'm going to break my piece of data into only 10 pieces and structure it such that any 14 of the 10 can reconstruct my data. So I'm going to set my K to 14. Now, as I'm pulling objects from different places, those objects are relatively large. But if I'm losing objects and things are getting corrupted, it's going to be hard for me to reconstruct them because I need some independent 10 of the 14 to exist in the world for me to be able to reconstruct. So this tends to work very well if there's a small number of nodes. If I am dividing my content amongst, say, Akamai servers, and there's only 20 servers in the world that are serving my content, I don't need a particularly large K. If I have some distributed hash table where I really want to spray my data across thousands of nodes, and those nodes are like web browsers that are coming up and going down and coming up and going down, coming up and going down, like crazy harsh environment, I'm much better off saying, oh, I'm going to break my piece of data into 3,010 pieces and spray it across this network. And now I say, well, I only need 2,150 of them to still be up, and I could have hundreds of nodes that went away between when I stored it and when I tried to retrieve it, and still be able to retrieve it. So it's really a question of independence. If I'm in a world where I've got 3 independent data centers, very small Ks are acceptable. If I'm in a world where I have much flakier but much larger independence, I've got thousands of web browsers as opposed to a small number of data centers, I'm going to want a much wider code, even if it's the same amount of redundancy. In both of these cases, it's 1.4 copies of the file that exist in the world. But the one with the large code is much more robust and much less likely to fail, again, assuming I have lots of independent devices. If I only have 3 data centers and I make thousands of copies of my code and one of the data centers goes down, it's still going to take out a third of my file, and I'm going to have to deal with that loss. So if something correlates all those failures back together, you didn't get your advantage of breaking it up. The recommendation in this paper is that you set your size such that each of your symbols fits in a single packet. Because for the most part on the internet, either a packet gets delivered or a packet doesn't get delivered. So if I break it all the way down to individual packets and those packets are independent, now I can spray these things across a network and reassemble them on the other side. And that will use more CPU than a very small code. But we get the added benefit of any single packet being taken out. I'm not going to be like, oh, I've got this 10 meg symbol that just got taken out because I'm missing one packet in the middle. All right, so let's do an evaluation. We had a bunch of objectives at the beginning. Let's see how we did. First is signaling overhead. The signaling overhead is very low. Each packet needs to have an identifier on it to say, which one of my fountain codes am I? What is that actual sequence of present or not present for each of my symbols to do the XOR to solve the algebra? But if you imagine something with, say, 20 symbols, that's only 20 bits of information. If you imagine something with thousands of symbols, we turn slightly and say, okay, well, now I'm going to pick some pseudo-random number generator. Let's say I seed it with a 32-bit symbol, and now that's going to give me a sequence of ones and zeros, or if I chunk it by bytes, a sequence of bytes to do the 255 add. I can get my entire sequence of what I'm adding and how many times I'm adding it from a pseudo-random seed. So set that to be 32 bits, and you've got 4 billion possible objects. Set it to be 64 bits. You've got an immense number of objects. Like, we just don't need that much metadata. So there's not a lot of signaling overhead. Even with a permutation identifier where I say, hey, please give me some packets. And by the way, I would like those packets to be from this particular permutation identifier. That permutation identifier can also be a small number that just feeds into the pseudo-random number generator. The second is latency overheads. Latency overheads is where I think this network protocol really shines. TCP is constantly stopping and asking for retransmissions and fixing things up. And a store and forward has to receive the entire object before it starts sending the object forward again. this really does feel like the best of both worlds to me, because for individual packets, it's a really cheap store and forward. Receive one packet, send the packet. Receive one packet, send the packet. And I don't need to keep track of a whole bunch of things to say, oh, I missed a packet, go back 16, resend all that. I just say, hey, I got 99%, send me an additional 1%, and it will send you a few more packets. And those will be unique packets, and you know those packets are helpful. So it doesn't actually care which packets you got or which packets you lost. It is in some sense a lower signaling overhead than TCP. The latency is going straight through. If there's no loss, this is as fast as any TCP could possibly be. If there is some loss, it's going to recover faster because I can do math to fix it. I don't have to use the speed of light to go back and fix things. And if I don't get enough packets to fix it and I have to say, hey, up the amount of redundancy you're sending me, I only have to go back one hop. I don't have to go all the way back to the beginning. So latency is a big win over what we've seen today in a TCP-like system. Security overhead. So there's a fair amount of security overhead here because not only do we have on each object a HMAC to make sure that it hasn't gotten corrupted, we also have on each packet an HMAC. So this is going to add an extra, say, 32 bytes of overhead to every single packet so that each packet can be HMAC'd and I can trust that that particular packet has not been forged. But even that, I think, is pretty cheap because before, when you had some TCP-like thing and you were going back and replaying any packet that managed to fail its checksum, now if I have a packet that fails its checksum, I can just throw it away and trust the next packet because I got a few extra packets. People, if you're on average encoding to 101% of the size of the file, things are just going to be recovered. So it is going to use a little bit more bandwidth, and it's probably going to use a little bit more processing because I'm checking both an HMAC on every packet and I'm checking an HMAC on the entire object when I'm done, but it's relatively cheap and gives you a security that is equivalent to, say, a TLS on top of TCP, where in TLS, we signed the channel and negotiated a whole handshake and three-way thing. Here, it's just you requested an object, that object signed, the signature is valid. I don't have to do some three-way handshake. I don't even necessarily even need a back channel. If there is someone who is just sending data at me and I have no way to say anything to them because it's like a satellite that's raining data down on the entire area, as long as I received enough objects to reproduce the object, I can check the signature, I can know it's valid and not need to have a conversation with the publisher node. And last, we have storage overheads. Unlike something where I have a regular store and forward from named data networking, here, I download an object. Once I get to 100% of the object, even if there was an extra 30% that came at me, I can certainly pass that through if I've got someone who's ready for it rather than doing the math to generate my own objects, but I don't need to store it. As I have built up the objects and I've solved my math puzzle and I have the true bytes of the object, I no longer have any need to store all of these fountain codes. I can just store the object. My caching never gets to be more than 100%. But it can also do better in storage overheads, because if I'm willing to divide it and say, hey, what I want in my network is a whole bunch of nodes that each store chunks of the file. With a normal store and forward, I had to have 1 copy or 2 copies or 3 copies. Now I could say I want 1.4 copies on the internet. And that's a totally feasible thing to do, to say I want 1.4 copies in the network, and only when someone tries to retrieve it will they reassemble the packet. So I think we've done a lot better, and that this could really outperform TCP in a lot of different scenarios that are latency sensitive or very asymmetric channels where the down is much more bandwidth than the up. It enables us to use multipath channels that we were not able to use under TCP because it just couldn't handle it because of head-of-line blocking problems that just don't appear here. I feel like this offers a lot of win over other systems. So this is why I love this paper, and it really inspires me as we can do better. I see all these people and it's like, oh, we have HTTP, and then we got HTTP 2 over quick. And Quick enabled us to do some things that solved head-of-line blocking. And HTTP2 says, I can send you object A and I can send you object B. And if you're missing a packet in object A, I can start sending you packets for object B while this is being retransmitted. And it sort of solves the head-of-line blocking by just giving you a bunch of lines, and only one of the lines gets blocked at a time. This kind of solution, I think, is a much more robust solution to head-of-line blocking and security and compression and dealing with low bandwidth problems. So basically, my proposal is when it's time for HTTP3, it should be sending its HTTP requests and response objects through a protocol that looks much more like this and much less like the TCP we have today, or Quick protocol, or TLS for security. Let's just actually sign our objects, let people move sign objects around the internet, and make our requests much more robust. Does anyone have questions? Y'all have to have questions. That's where the fun part comes from.
Yeah, I got a question. Probably gonna show my general ignorance of networking here, but so when you're talking about like nodes in the network graph storing copies of these objects, sometimes you would also, or it seemed like you would also use the word file sometimes, or object, and then sometimes we would talk about packets. And I guess I'm trying to form an intuition for like, what are the resource requirements on these nodes? Are these like little, can these be little routers, or do they need to be like big nodes that can like do CDN caching? Or like, I guess I'm a little confused about what object, file, and like really means.
Yeah, so there's a few answers there. If you have a very big node and you want to do an Akamai style, this is a point of presence where we've got 6 racks of servers that have a meaningful chunk of the entire Netflix library. You certainly could do that, and requests for objects, because they're routing by object ID, would hit those big heavy nodes, and those nodes would be able to serve your content. With the advantage that they don't need to have, say, the certificate for Netflix. You know, today, if someone wants to have a CDN that's got a meaningful chunk of Netflix, it's got to have the TLS cert for Netflix because that's the only way you can open the channel. Whereas here, that node is signing all of the packets it generates with itself, but the object trust comes from the hash that is once you have reassembled the entire object. Those chunks are likely to be relatively small. You probably don't want the chunk to be a 1 gigabyte movie as an object that has an object ID. You probably want it to be an 128 kilobyte or 10 megabyte 3-second chunk of the movie. So you can say, oh, give me the first chunk, give me the second chunk, give me, 30-second chunks of a video make a much better object here than, say, the entire video file, mainly because people want to finish getting all of the parts and reassemble something in a reasonable amount of time. However, if you try to go all the way to the other end and say, let's say in your home, you've got a crummy little Linksys box. One of the problems we have with crummy home routers is they now have 2 gigs of memory in them because memory is cheap and the smallest memory chip you can get is 2 gigs. And they've been making giant TCP buffers that buffer up all kinds of data. And that makes TCP run super slowly as you're waiting for everything to run through the buffer. If you took that same device and said, hey, I'm going to store these objects in memory, and I'm just going to fill in my 10 megabyte object and put that entire thing in memory and use the crummy little CPU that is on that Linksys box to reassemble the file and start sending it down. Well, now if I've got, say, 5 computers in my house that all want to download the Windows update on the same Tuesday for some reason, they can each talk to my home router, and my home router can say, oh yeah, I've totally got that stream and can send it to you. And if I get a cheap hard drive and plug in 5 terabytes of storage for $100 into the USB port on the back of that crummy router, it can now store an enormous amount of the objects that come in and say, okay, well, cache the last 5 terabytes of objects that came into my system. And now when somebody tries to do a Windows update, of course it's already there. Or you try to watch Gangnam Style again, and it's like, oh yeah, I remember Gangnam Style. I've already got all the chunks you need for the YouTube video. Let me just hand them to you. So one of the things I really like about content-centric networking is you kind of can store anything anywhere, and it depends on the resources you have. It totally makes sense to plug a multi-terabyte hard drive into your home router that is going to store only the objects you already downloaded into your home to serve them to you again if you need them, or from a different computer. And it makes sense for really heavy metal. I've got 6 racks here that are all going to store a large amount of content for an entire ISP to be able to get that caching efficiency, because the ISP doesn't want to peer with its neighbors. So it says, okay, I'm going to run this node purely for selfish reasons, so I don't have to pay as much in bandwidth costs. I'm going to set up 6 racks in each of the regions in which I operate. Once something's in my network, I'm going to cache that object, and then I'm going to serve it to my users. We're going to get much lower latency and higher bandwidth and a generally better experience, but also cost the ISP less in peering costs. Does that make sense?
Yeah, totally. Thanks. That fills in a lot of like little bits that I was confused about. But yeah, thanks. Thanks. And great talk.
One of the reasons I like it is I think right now, most ISPs are caching Netflix, because Netflix has a program to say, don't want to get crushed by Netflix customers? Give us a few racks and we'll send you servers and we'll put the things there and we're going to not crush you. This enables that same kind of technology to be accessible to any website in the world, because the ISPs, for purely selfish reasons, will say, hey, I'm going to run a few racks and I'm going to cache whatever is actually popular in my network so that I don't have to keep downloading it and keep paying that peering costs. Now we get a much more neutral network than the network we have today, which fundamentally you can make the kind of caching deals with Netflix, and you can't make the kind of caching deals with a random website that just started up yesterday, because you don't have the TLS cert. Like, the security choices we've made to say TLS, we're going to sign the connections and not the content, means you can't just store and serve content anywhere. And if we switch to say, instead of signing connections, let's sign content, now we can play these games where anyone can set up a cache and get the benefit from that, whether you're an ISP that doesn't want to talk to a business, or whether it's your own home router and you just don't want to interact with someone else.
So I just want to understand this. You suggested like multiple nodes carrying multiple sets of data, random data.
Sure.
So it means that you set up connections with each of those nodes when you want different sets of data. So like, isn't that going to be another additional cost, just setting up connection?
So if we look at the, say, tree structure, in this case, the top 2 nodes here each have a connection with the publisher node. So the publisher is sending the file to both of those nodes and is going to have those 2 connections open, but doesn't have to have a connection open with the 4 at the bottom, the 4 next to layer, or the 8 at the bottom layer. So the publisher node only needs to seed someone in the network with the content. So if content is very unpopular, you may put only fractional reserves. So you talk to a bunch of nodes and say, you get a third of the file, and you get a third of the file, and you get a third of the file, and you get a third of the file. And I've stuck a third of the file on 4 nodes. And now anyone who wants to download it is going to have to talk to 3 of the 4 nodes. But if I have content that is super popular, I just got slash dotted and literally a million nodes are all trying to download my content simultaneously, I can't serve a million nodes off of my Raspberry Pi. In the TLS world, I just lose that game and my node goes down because it got too popular. In a liquid data world, I say, okay, I am going to connect to a couple of big content caches. I'm going to connect to Akamai, and I'm going to connect to Google, and I'm going to connect to Amazon, and I'm going to hand these big nodes copies of my file. And because there's a lot of files and lots of people are searching for it, they're going to hit all those people. And then smaller nodes are going to cache it. And then even smaller nodes are going to cache it. And eventually you're going to end up with lots of copies all around the internet. And I can turn off my Raspberry Pi and my content will still continue to be distributed around the internet as long as one of the nodes in the network thinks it's interesting to cache and is still willing to serve it.
Sorry, I didn't get it correctly, but like you're distributing data, you're splitting the data also, right? Like
yes.
so multiple nodes can serve multiple different sections of the data. So my question was like, there are going to be more connections depending upon the size of the data being cached, right? Like if it's like a 10 terabyte thing and I'm trying to download it, I'll be hitting these many servers to get that file. So like number of connections actually increases, right?
You're thinking of this pattern where say I am trying to download a fourth of the file from 4 of the 8 different nodes.
Yep.
In that case, the number of connections will increase because there is no node that has the entirety of the file here. So when you try to go get that object and recover that object, you are actually going to pick 4 of these 8 nodes and go to each of them and say, hey, give me as much of this file as you've got. And each of them will say, oh, I've only got a quarter of the file. Here's a quarter of the file. And once it adds up to more than 100%, then you're going to be able to recover the object.
Yeah.
But yes, that can increase the number of connections.
I have a question. So we during this presentation, you talked mainly about like large objects, large blobs of data that are we want to deliver from point A to B. So is there a point, or is there a specific size that just makes this like significantly better versus just using TCP? Because I understand this start to make sense only when the data is large enough. If it's too small, it's just like probably the benefit would not be as significant as with larger data. And the other question I have related to that as well is if we think about that tree structure, we think about some source, we think about some middleware or middle nodes that are transmitting the data. Usually the problem with connectivity is somewhere near the last mile or near the end user. Those are like usually the most affected by all sorts of retransmissions or all sorts of TCP issues.
Yes, the connection between you and your modem is almost always worse than modem and Google.
Is there like a specific conditions when this will be working better or when it will not be working better? Like what are the like how bad the line or how bad the connection needs to be when it doesn't really matter what you will use, you will still like suffer?
Yeah, so I think both questions come down a little bit to the large code, small code question.
Yeah.
So if I decide I want a K of 10 and say any 10 of these objects are going to be able to reconstruct what I am building right now, then I'm going to be able to do something like I'm going to pick 14 servers and I'm going to make 14 chunks of size 1/10 of my object and spread that thing around. I want to make sure that each of my symbols is meaningfully large relative to the size of a packet. So I probably don't want to use that structure until my object is at least, say, 140 kilobytes. Because each one of my packets is going to be about 1.4 kilobytes, and I need to have at least 10 times that to be able to encode it. If I'm in a network where I've got lots of nodes and I want to have a 1,000-way code, well, now that's 1,000 times my 1.4 kilobyte packet. So now I'm going to start playing games of like, okay, maybe 128 kilobytes is the smallest chunk where it's going to make sense to start encoding these things in these ways. I probably wouldn't want to go much larger than, say, 32 megabytes. And I would say, okay, at 32 megabytes, if you have a file that is larger than 32 megabytes, you're probably better off saying, I'm going to split it into chunks. And each of those chunks, I'm going to do this kind of erasure coding on, so that people don't have to download too much data before they start recovering the object. But if I were to guess, I would say the sweet spot is probably around 128 kilobits for each object size. As for the where do you get the most benefit by breaking things down, I would say practically most of the errors that you're going to see are between your modem and your computer, because Wi-Fi is noisy and lossy and problematic, and people do things like stand 100 meters away from their Wi-Fi router and hope that it works and turn on microwaves, and like Wi-Fi is messy in a way that the copper that connects you to your ISP is much better than that. It's like 10 to the minus 9th packet loss on the copper to your ISP and 10 to the minus 12th loss in the fiber that connects your ISP to the rest of the internet. So probably where you want to end up here is something like, I am going to encode to 101% of the size of my file. I'm going to send that down from the source object. It's going to essentially be reconstructed at your modem without any loss in the middle. And then your modem is going to generate new fountain code objects for your computer. So I think it will work particularly well in that case where all the noise is at the end, because suddenly your particular Wi-Fi router can do a lot of the repair and retransmission itself, that in a TCP world, that transmission will go all the way back to the server that owned the data and then all the way back to you because you dropped a packet. Now that recovery is, you talk to your Wi-Fi router and say, I'm sorry, I'm seeing a slightly higher error rate now. Please up the amount of over encoding that you are doing so that I can get enough forward error correction to fix it.
All right. Sounds good. Thank you.
All right. With that, I will stop the recording.